Hello! In this video, I'll be going over adders, because it's a tricky topic. Now, the purpose of an adder is to add a couple of binary bits together to get some outputs. In this case here, we're adding P and Q to W and X to get some 1, some 2, and a carry bit as our outputs. In this class, there are 4 types of adders we'll be going through. The half adder, the full adder, the 2-bit adder, and the n-bit adder. I'll be going through these one by one. Now, back to the original purpose, adding binary bits together to get an output. Let's make an example. So let's say P and Q is 1, 1. Oh, wrong color. Let's say P and Q are 1, 1, and WX are 1 and 0. So we're adding 1, 1 to 1, 0. So 1 plus 0 is going to be 1, and the carry bit resulting from that is going to be 0. So now, in our next thing, we want to add 0, 1, and 1. 1, 1 being the 2 inputs that are the 2 original inputs, and 0 being the carry bit that was created from adding 1 and 0 together from the right column. So 0 plus 1 is going to give us 0, 1. So the answer for this, the output, is going to be 101 from adding 1, 1 and 1, 0. Now, as you can see, the first step we want to do is we're going to want to add these 2 inputs first. We first added 1 and 0 together to get this sum bit 1 and this carry bit 0. 2 inputs, 2 outputs. Now that is what the half adder does. The half adder takes 2 inputs and gives us 2 outputs, 1 sum bit and 1 carry bit. So in this example, I'll be using the variables x and y. X plus y is going to give us a sum bit and a carry bit. Since there's only 2 inputs and they're both binary bits, we can draw out a truth table for them. So xy 0, 0, 1, 1, 0, 1, 0, 1 for y. And the sum bit here, carry bit here. What we're doing here is we're adding these to get the sum bit and carry bit. So taking x and taking y, we're going to first add 0. We're going to add to 0. So 0 plus 0 is going to give us 0 for the sum bit and 0 for the carry bit. To illustrate, it's going to look like this. X is 0, y is 0, sum is 0, carry bit that carries over is also 0. Next one, 0, 1. 0 plus 1, 1, 0. So 1 plus 0, 1, 0. 1 plus 1, this is going to give us 0, 1. Because the next bit carries over. Now, the columns for the sum bit and the carry bit should look familiar to you all. That's because they're similar to operators we've seen before. Carry is a bit easier to see. 0, 0, 0, 1 is the same as the truth table column for the AND. So this is equivalent to x and y. And for the sum bit, this is x XOR y. Thus, we know we can draw the digital circuit as x ANDed with y to return the carry bit, and x XORed with y to give us the sum bit. Now, in this class, we're not going to use this XOR operator, because instead we can write the half adder gate as x, y. As usual, carry is just x and y ended together, carry, and then we can replace the XOR with one OR gate, one NOT gate, and another AND gate. So instead, we have 2 AND gates, 1 OR gate, and 1 NOT gate. If we write this out using a Boolean formula, we write this as, C is going to be expressed as x and y, and sum is going to be expressed as x or y. I'll move this so it's clear to see. There's more room. X or y, and it with not x and y. And this makes logical sense, because either or means x or y holds true, except for the case where x and y both hold true. So it's x or y, except for the case where they both hold true. So this is I'll highlight it. This is the half adder gate that we have constructed. Alright, going back over here, we can now add 1 and 0, well, q and x. We can add q and x, and we return some 1 and a carry bit, a temporary carry bit from the half adder. Now, instead of having 2 inputs, like the q and x returning some 1 and carry 1, we need to add 3 inputs together now. Carry from the half adder with P and W. So now there are 3 inputs, and we want to output two outputs, sum 2 and a final carry bit. This is what the full adder is for. Full adders take 3 inputs and output 2 outputs. So in this case, we're adding C, P, W to get a sum 2 and a final carry bit. I'll just use the variables P, Q, and R to get a sum bit and a carry bit. Now, full adders are a bit more difficult than half adders, but the principle is the same. We already have the half adder, an adder that can take 2 inputs, add them together to get 2 outputs. So for the full adder, we're just going to use 2 steps and break it down. Step 1, we're going to use a half adder to add P and Q. Breaking down the problem, we're just going to add P and Q together first. So P and Q, going to black box the half adder, returns a sum bit, temporary sum bit, and a temporary carry bit here, and a sum bit here as well. Next, we want to take the results from P plus Q and add it to R. So step 2, add to R. So we're going to take the sum bit we got from adding P and Q and just add it to R. Again, half adder has 2 inputs, gives 2 outputs. So half adder here, we get a final sum bit here, and we also get another temporary carry bit. I will label as C2. So then we're just going to OR carry 1 and carry 2 together to get the final carry bit. And this is what a full adder looks like. Now, why are we using the OR gate here to OR carry 1 and carry 2? That's because carry 1 and carry 2 can never both be 1 at the same time. They can either be 0, 0, 1, 0, 0, 1, but never 1 and 1. Because of that, as long as one of them are 1, we know it's going to return the final carry bit as 1, otherwise it would just be 0, which is why we're ORing them together. Now, if you want to understand why both of them can never be 1 at the same time, think through a couple of problems. The maximum inputs we can have for P, Q, and R are all 1, because 1 is the maximum digit in binary. So 1 plus 1 plus 1. And this will ensure we get the maximum possible output. Let's go through the gates together using this example. So 1 plus 1. This is our P and Q. P and Q, 1, 1 goes to the half adder, and we're gonna get 1 for the sum, 0 for the sum bit. 1 plus 1, 0, 1, and 1 for the temporary carry bit. So then 0, 1 go down, you gotta add 0 here to R. So 0 and R then added together, 0 plus 1, R being this thing. And you get, using the half adder, you get a sum bit as 1 and the final carry bit as another temporary carry bit as 0. So this is going to be 1, output as 1, and this carry bit here is going to be 0. Notice how this is 1 and how this is 0, and both of them are not 1 at the same time. None of the cases possible will ever give you 2 temporary carry bits that are both 1. So then 1 and 0 OR together, and the final carry bit here is just going to be 1. So 1 plus 1 plus 1 is going to give you 1, 1, which is 3 in base 10. And that is how the full adder works, by using 2 half adders and 1 OR operator. Now that we've explained the full adder and the half adder, we have 2 ways of adding. We have a way of adding 2 inputs to get 2 outputs, and a way of adding 3 inputs to get 2 outputs. But now we must combine the 2 in order to get the 2-bit adder, which can add all of these inputs to get these outputs. The 2-bit adder builds on what we already know, which is the half adder and the full adder, just like how the full adder builds on the half adder. So we have P, Q, W, X to get sum 1, sum 2, and a carry bit. Q and X, we already know that we use the half adder to add these together to get sum 1 and a temporary carry bit here. And we know we can use a full adder, which I will use blue to show, to add the carry 1 from the half adder to P and W to get sum 2 and the final carry. So let's draw out the gate for this. Let's just start with Q and X. We already know what to do with them. We use Q and X, put them in a half adder. It returns sum 1 and carry 1, the temporary carry bit. Sum 1, we've already got it, so we can just put it all the way to the end. Now, we know we want to add the carry bit to P and W. So, P, W. Well, it just so happens that the full header has 3 inputs, so it all works out. We add carry 1 to P and W. And this just gives us sum 2 and the final carry. So the 2-bit adder just uses what we already know and combines it all together. That's all there is to it. The n-bit adder is just building on the 2-bit adder again. You understand already how this works. The first two, let's put in another example. A, B, C, D plus E, F, G, H to give us a final carry bit, and then sum 1, sum 2, sum 3, sum 4. The logic is the same as always. You add the first two D and H using a half adder. This gives us the sum bit and a temporary carry bit. Then we use a full adder to add 3 inputs together, the carry from the half adder, with C and G to get us the second sum bit and another carry bit. Use another half adder to add these together to get a third sum bit and then another temporary carry bit, which we use a final full adder to add these 3 together to get another sum bit and the final carry bit. So it's just really an extended version of the 2-bit adder. Let's draw this out. D and H, half adder, and you just get sum 1. It returns a temporary carry 1, which we will add to C and G, which we'll use a full adder for. This full adder gives us the second sum and another carry bit, which we will just keep on adding. So then this is going to be added to B and F. Excuse my handwriting. Gives us another sum 3. And then B and F, its carry bit, is added to A and E. Which will be put into another full adder to give us the final sum 4 and the final carry bit. And this here is our output. So in the n-bit adder, there are 4 bits here, and let's count the number of full adders. We have 1, 2, 3 full adders. There's n-1 full adders plus 1 original half adder to create an n-bit adder. And as you can imagine, as you have more bits, the adders just get larger and larger. So this is basically how adders work.